A wind tunnel is a tool used in aerodynamic research to study the effects of air moving past solid objects. A wind tunnel consists of a tubular passage with the object under test mounted in the middle. Air is made to move past the object by a powerful fan system or other means. The test object, often called a wind tunnel model, is instrumented with suitable sensors to measure aerodynamic forces, pressure distribution, or other aerodynamic-related characteristics. The earliest wind tunnels were invented towards the end of the 19th century, in the early days of aeronautic research, when many attempted to develop successful heavier-than-air flying machines. The wind tunnel was envisioned as a means of reversing the usual paradigm. Instead of the air standing still and an object moving at speed through it, the same effect would be obtained if the object stood still and the air moved at speed past it. In that way, a stationary observer could study the flying object in action, and could measure the aerodynamic forces being imposed on it. The development of wind tunnels accompanied the development of the airplane. Large wind tunnels were built during the Second World War. Wind tunnel testing was considered of strategic importance during the Cold War development of supersonic aircraft and missiles. Later on, wind tunnel study came into its own. The effects of wind on man-made structures or objects needed to be studied when buildings became tall enough to present large surfaces to the wind, and the resulting forces had to be resisted by the building's internal structure. Determining such forces was required before building codes could specify the required strength of such buildings, and such tests continue to be used for large or unusual buildings. Still later, wind tunnel testing was applied to automobiles, not so much to determine aerodynamic forces per se, but more to determine ways to reduce the power required to move the vehicle on roadways at a given speed. In these studies, the interaction between the road and the vehicle plays a significant role, and this interaction must be taken into consideration when interpreting the test results. In an actual situation, the roadway is moving relative to the vehicle, but the air is stationary relative to the roadway. But in the wind tunnel, the air is moving relative to the roadway, while the roadway is stationary relative to the test vehicle. Some automotive test wind tunnels have incorporated moving belts under the test vehicle in an effort to approximate the actual condition, and very similar devices are used in wind tunnel testing of aircraft takeoff and landing configurations. The advances in computational fluid dynamics modeling on high-speed digital computers has reduced the demand for wind tunnel testing. However, CFD results are still not completely reliable, and wind tunnels are used to verify CFD predictions. Measurement of aerodynamic forces. Air velocity and pressures are measured in several ways in wind tunnels. Air velocity through the test section is determined by Bernoulli's principle. Measurement of the dynamic pressure, the static pressure, and the temperature rise in the airflow. The direction of airflow around a model can be determined by tufts of yarn attached to the aerodynamic surfaces. The direction of airflow approaching a surface can be visualized by mounting threads in the airflow ahead of and aft of the test model. Smoke or bubbles of liquid can be introduced into the airflow upstream of the test model, and their path around the model can be photographed. Aerodynamic forces on the test model are usually measured with beam balances, connected to the test model with beams, strings, or cables. The pressure distributions across the test model have historically been measured by drilling many small holes along the airflow path, and using multi-tube manometers to measure the pressure at each hole. Pressure distributions can more conveniently be measured by the use of pressure-sensitive paint, in which higher local pressure is indicated by lowered fluorescence of the paint at that point. Pressure distributions can also be conveniently measured by the use of pressure-sensitive pressure belts, a recent development in which multiple ultra-miniaturized pressure sensor modules are integrated into a flexible strip. The strip is attached to the aerodynamic surface with tape, and it sends signals depicting the pressure distribution along its surface. Pressure distributions on a test model can also be determined by performing a wake survey, in which either a single pitot tube is used to obtain multiple readings downstream of the test model, or a multiple tube manometer is mounted downstream and all its readings are taken. The aerodynamic properties of an object cannot all remain the same for a scaled model. However, by observing certain similarity rules, a very satisfactory correspondence between the aerodynamic properties of a scaled model and a full-size object can be achieved. The choice of similarity parameters depends on the purpose of the test, but the most important conditions to satisfy are usually geometric similarity. All dimensions of the object must be proportionally scaled. Mach number. The ratio of the airspeed to the speed of sound should be identical for the scaled model and the actual object. Reynolds number. The ratio of inertial forces to viscous forces should be kept. This parameter is difficult to satisfy with a scaled model and has led to development of pressurized and cryogenic wind tunnels in which the viscosity of the working fluid can be greatly changed to compensate for the reduced scale of the model. In certain particular test cases, other similarity parameters must be satisfied, such as e.g. Froude number. History. Origins. English military engineer and mathematician Benjamin Robbins invented a whirling arm apparatus to determine drag and did some of the first experiments in aviation theory. Sir George Cayley also used a whirling arm to measure the drag and lift of various airfoils. His whirling arm was 5 feet long and attained top speeds between 10 and 20 feet per second. However, the whirling arm does not produce a reliable flow of air impacting the test shape at a normal incidence. Centrifugal forces and the fact that the object is moving in its own wake mean that detailed examination of the airflow is difficult. Francis Herbert Wenham, a council member of the Aeronautical Society of Great Britain, addressed these issues by inventing, designing and operating the first enclosed wind tunnel in 1871. Once this breakthrough had been achieved, detailed technical data was rapidly extracted by the use of this tool. Wenham and his colleague Browning are credited with many fundamental discoveries, including the measurement of L-D ratios, and the revelation of the beneficial effects of a high aspect ratio. Konstantin Tsiolkovsky built an open-section wind tunnel with a centrifugal blower in 1897, and determined the drag coefficients of flat plates, cylinders and spheres. Danish inventor Poul Larcour applied wind tunnels in his process of developing and refining the technology of wind turbines in the early 1890s. Carl Richard Nyberg used a wind tunnel when designing his Fluggen from 1897 and onwards. In a classic set of experiments, the Englishman Osborne Reynolds of the University of Manchester demonstrated that the airflow pattern over a scale model would be the same for the full-scale vehicle if a certain flow parameter were the same in both cases. This factor, now known as the Reynolds number, is a basic parameter in the description of all fluid flow situations, including the shapes of flow patterns, the ease of heat transfer, and the onset of turbulence. This comprises the central scientific justification for the use of models in wind tunnels to simulate real-life phenomena. However, there are limitations on conditions in which dynamic similarity is based upon the Reynolds number alone. The Wright brothers' use of a simple wind tunnel in 1901 to study the effects of airflow over various shapes while developing their Wright Flyer was, in some ways, revolutionary. It can be seen from the above, however, that they were simply using the accepted technology of the day, though this was not yet a common technology in America. In France, Gustav Eiffel built his first open-return wind tunnel in 1909, powered by a 50 kW electric motor, at Champs-de-Mars, near the foot of the tower that bears his name. In 1912, Eiffel's laboratory was moved to Auteuil, a suburb of Paris, where his wind tunnel with a 2-meter test section is still operational today. Eiffel significantly improved the efficiency of the open return wind tunnel by enclosing the test section in a chamber, designing a flared inlet with a honeycomb flow straighter and adding a diffuser between the test section and the fan located at the downstream end of the diffuser. This was an arrangement followed by a number of wind tunnels later built. In fact, the open return low-speed wind tunnel is often called the Eiffel-type wind tunnel. Subsequent use of wind tunnels proliferated as the science of aerodynamics and discipline of aeronautical engineering were established and air travel and power were developed. The U.S. Navy in 1916 built one of the largest wind tunnels in the world at that time at the Washington Navy Yard. The inlet was almost 11 feet in diameter and the discharge part was 7 feet in diameter. A 500 horsepower electric motor drove the paddle-type fan blades. In 1931, the NACA built a 30-foot by 60-foot full-scale wind tunnel at Langley Research Center in Langley, Virginia. The tunnel was powered by a pair of fans driven by 4,000 horsepower electric motors. The layout was a double-return, closed-loop format and could accommodate many full-size real aircraft as well as scale models. The tunnel was eventually closed and, even though it was declared a historic national landmark in 1995, demolition began in 2010. Until World War II, the world's largest wind tunnel was built in 1932 to 1934 and located in a suburb of Paris, Chalais-Meudon, France. It was designed to test full-size aircraft and had 6 large fans driven by high-powered electric motors. The Chalais-Meudon wind tunnel was used by ONERA under the name S1CH until 1976, e.g., in the development of the Caravelle and Concorde airplanes. Today, this wind tunnel is preserved as a national monument. World War II. In 1941, the U.S. constructed one of the largest wind tunnels at that time at Wright Field in Dayton, Ohio. This wind tunnel starts at 45 feet and narrows to 20 feet in diameter. 2 40-foot fans were driven by a 40,000 horsepower electric motor. Large-scale aircraft models could be tested at airspeeds of 400 miles per hour. The wind tunnel used by German scientists at Peenemünde prior to and during World War II is an interesting example of the difficulties associated with extending the useful range of large wind tunnels. It used some large natural caves which were increased in size by excavation and then sealed to store large volumes of air which could then be routed through the wind tunnels. This innovative approach allowed lab research in high-speed regimes and greatly accelerated the rate of advance of Germany's aeronautical engineering efforts. By the end of the war, Germany had at least 3 different supersonic wind tunnels, with one capable of Mach 4.4 airflows. A large wind tunnel under construction near Utztal, Austria would have had 2 fans directly driven by 2 50,000 horsepower hydraulic turbines. The installation was not completed by the end of the war and the dismantled equipment was shipped to Modane, France in 1946, where it was re-erected and is still operated there by the ONERA. With its 8 meters test section and airspeed up to Mach 1, it is the largest transonic wind tunnel facility in the world. On June 22, 1942, Curtiss-Wright financed construction of one of the nation's largest subsonic wind tunnels in Buffalo, New York. The first concrete for building was poured on June 22, 1942 on a site that eventually would become Calspan, where the largest independently owned wind tunnel in the United States still operates. By the end of World War II, the U.S. had built 8 new wind tunnels, including the largest one in the world at Moffett Field near Sunnyvale, California, which was designed to test full-size aircraft at speeds of less than 250 miles per hour, and a vertical wind tunnel at Wright Field, Ohio, where the wind stream is upwards for the testing of models in spin situations and the concepts and engineering designs for the first primitive helicopters flown in the U.S. Post-World War II, later research into airflows near or above the speed of sound used a related approach. Metal pressure chambers were used to store high-pressure air, which was then accelerated through a nozzle designed to provide supersonic flow. The observation or instrumentation chamber was then placed at the proper location in the throat or nozzle for the desired airspeed. In the United States, concern over the lagging of American research facilities compared to those built by the Germans led to the Unitary Wind Tunnel Plan Act of 1949, which authorized expenditure to construct new wind tunnels at universities and at military sites. Some German wartime wind tunnels were dismantled for shipment to the United States as part of the plan to exploit German technology developments. For limited applications, computational fluid dynamics can supplement or possibly replace the use of wind tunnels. For example, the experimental rocket plane Spaceship ONE was designed without any use of wind tunnels. However, on one test, flight threads were attached to the surface of the wings, performing a wind tunnel type of test during an actual flight in order to refine the computational model. Where external turbulent flow is present, CFD is not practical due to limitations in present-day computing resources. For example, an area that is still much too complex for the use of CFD is determining the effects of flow on and around structures, bridges, terrain, etc. The most effective way to simulate external turbulent flow is through the use of a boundary layer wind tunnel. There are many applications for boundary layer wind tunnel modeling. For example, understanding the impact of wind on high-rise buildings, factories, bridges, etc., can help building designers construct a structure that stands up to wind effects in the most efficient manner possible. Another significant application for boundary layer wind tunnel modeling is for understanding exhaust gas dispersion patterns for hospitals, laboratories, and other emitting sources. Other examples of boundary layer wind tunnel applications are assessments of pedestrian comfort and snow drifting. Wind tunnel modeling is accepted as a method for aiding in green building design. For instance, the use of boundary layer wind tunnel modeling can be used as a credit for leadership in energy and environmental design certification through the U.S. Green Building Council. Wind tunnel tests in a boundary layer wind tunnel allow for the natural drag of the Earth's surface to be simulated. For accuracy, it is important to simulate the mean wind speed profile and turbulence effects within the atmospheric boundary layer. Most codes and standards recognize that wind tunnel testing can produce reliable information for designers, especially when the projects are in complex terrain or on exposed sites. In the USA, many wind tunnels have been decommissioned in the last 20 years, including some historic facilities. Pressure is brought to bear on remaining wind tunnels due to declining or erratic usage, high electricity costs, and in some cases the high value of the real estate upon which the facility sits. On the other hand, CFD validation still requires wind tunnel data, and this is likely to be the case for the foreseeable future. Studies have been done and others are underway to assess future military and commercial wind tunnel needs, but the outcome remains uncertain. More recently, an increasing use of jet-powered, instrumented unmanned vehicles, research drones, have replaced some of the traditional uses of wind tunnels.